Okay, thank you very much, students. Today we are going to prove a very important theorem in group theory that is connected to subgroup and a group. Okay, suppose that H is a subgroup of G, then A comma B belongs to H implies A B belongs to H. That is one point. The second point is that if A belongs to H, then A inverse also belongs to H. So if H is a subgroup of G, then these two points are satisfied. Or if two points, that is, if A comma B belongs to H, AB belongs to H, and if A belongs to H, A inverse belongs to H, then H is the subgroup of G. Okay, so that's what we are going to prove today. Now look at the screen there. That's what we are going to prove here. Right. Now H is a subgroup of G. Then we have to prove that if A comma B belongs to H implies AB belongs to H, and A belongs to H implies A inverse also belongs to H. Okay, so this we can prove in a good way as follows. Now, see the picture here nearby. This is a G. I am taking this what a group, and this is a subset of G. We suppose that this is H. Right. Now what I have to prove that if H is a subgroup of G, then it has to satisfy these two conditions. Okay. Now forward proof I am proving now. So to prove the forward proof, what I have to prove is that um, we have to assume that H is a subgroup of G. Then we have to take any two elements. That implies the the association of the two elements with respect to the binary operation should belongs to the same H. That's what I have to prove. And second point, if A belongs to H, A inverse belongs to H. The 2 points that I have to prove now. Okay. So assume that H is a subgroup of G. Right. Now, or if that is the case, what we have to prove? We have to prove the second point. That A comma B belongs to H implies A B belongs to H, and A belongs to H implies A inverse also belongs to H. That's what we have to prove. Now look at this. H is a subset of G, or H is a subgroup of G. Suppose I am taking A. A is any element in H. So if A is an element in H implies A is an element in G also. So take another element B that also belongs to H. What is the meaning? Both A and B also elements of G. But what is G? G is a group. Okay. Therefore, AB should belongs to G. AB must belong to G by the commutative property or closure property. Okay, closure property. Sorry, by closure property, AB must belongs to G. But what is AB? Where AB is? AB is in H. Okay, therefore, definitely we can say that if A and B are any two elements in H, then um, they are the elements of G, and in G, the commutative law is true. Therefore, AB belongs to G. That implies AB also in H. Therefore, AB belongs to H. So that way we can prove. Okay. So this is a pictorial way we can prove, but the theoretical way, how we can prove that in a theoretical way, that's what we have to understand. Okay. So let me take the theoretical way I'm proving like this. um, Suppose, okay, that is, imagine that A comma B belongs to H. Implies what? Which implies what? A comma B belongs to G also, because the subset of H is a subset of G. So this implies AB belongs to G, and then which implies AB belongs to H also. So first we have proved the first conditions, so which implies one is proved. which implies 1 is proved there. Let me write 1 is proved. Yes. Now what about second one? Let us prove the second one. Okay. Right. Now what's the second one we have to prove is that if A belongs to H, A inverse also belongs to H. A inverse belongs to H. A inverse belongs to H. That's what we have to prove. Now let us take that. If A belongs to H, okay, now you understand that if A belongs to H implies A belongs to H implies what? Because H is the subset of G. Therefore, A belongs to H implies A belongs to G also. But what is G? G is a group. So in group, each and every element have its inverse. Therefore, A inverse must belongs to G. So which implies what? The A inverse where it must be? It must be in H. Okay. So the second condition is also satisfied. Okay. So if H is a subgroup, H is a subgroup of G, then we have proved that AB belongs to H implies AB belongs to H. A belongs to H implies A inverse belongs to H. Now the converse part, that's what we have to prove now. Okay. Okay. Take as the converse part now. The converse part is what? If these two conditions are satisfied, then H is a subgroup of G. Okay, that's what we have to prove. It's a converse part. So what's the converse part? The converse part is that if A comma B belongs to H, implies AB belongs to H. And if A belongs to H, A inverse belongs to H. So if this is true, then H is the subgroup of G. That's what we have to prove. So to prove that H is a subgroup of G, we have to prove that H is a group with respect to the operation we are defining on G. Okay, that is associative law we have to prove. And second one, identity, presence of the identity in H we have to prove. And third one, we have to prove each and every element have the inverse. So there are 3 points we have to prove: associativity, identity existence, and inverse existence for each and every activity, for every numbers there. That's what we have to prove now. Let's prove that now. Okay, right. Now assume, we have to assume first and second. Okay, so assume, we have to assume first and second. First and second factor is there. Then we have to prove the first fact. We have to prove that H is a subgroup of G. Okay, so let us prove that. Right. If A belongs to H, B belongs to H, implies AB belongs to H. Okay, so that's what's true there. Okay, now the associative law, we can say that if A comma B comma C belongs to H, suppose A comma B belongs to H, suppose, implies that all the elements are in G. Let me correct. So A comma B comma C also belongs to G. Because why? Because H is a subset of G. Therefore, all the elements in A, B, C, H also in G. Okay. But what is G? G is a group. So commutative law is satisfied there. Okay. Therefore, which implies associative law is satisfied. That is, A into BC equals AB into AC. So associative law is satisfied. Associative law is satisfied. Next, what we have to prove that the identity element, presence of the identity element in H. Okay, identity element in H. Okay, right. Let us take for example here. If A belongs to H, A belongs to H implies what? if A is any element in the set H, then A inverse also would be there in H. Am I correct? So that's what we have to see here. So if A belongs to H, implies A belongs to G, which implies A inverse belongs to G, which implies A inverse belongs to H. Okay, by the first the point given there, if A belongs to H, B belongs to H, AB belongs to H. Apply that idea, you'll get A into A inverse belongs to H. We assume the second condition. From the second condition, we see this. Okay, right. If A into A inverse belongs to H, that means what? By the definition of the group theory, if an element is associated with the inverse, you will get the identity element. So what we are getting is the identity element. So which implies the identity element belongs to H. B belongs to H. So what takes place here? What takes place here? The identity exists. That's what we are proving here. Okay. So first we proved that associative law is true in H. Second, we proved that existence of identity. Now remains to prove is that the inverse, each and every element have inverse. That's what we have proved. Okay. So let us prove that now. Now here I am proving here, no place there, therefore I am proving here. Okay. Now A belongs to H implies A inverse also belongs to H. Implies A into E belongs to H. A into E belongs to H because E is the identity in H. I mean that E is the identity in H. Therefore, if you take any element in H, that we can write it as the association of that particular element with E. Okay, that is possible here. Okay, so now look at this. This we can write it as A inverse into A inverse into A. We can write as that E that we can write belongs to A into A into A into E. We can write like this. Belongs to H. So which implies what? A inverse element, and that element also belongs to H. I mean, which implies here. Now here A inverse belongs to H. So for each and every element, we have that A inverse belongs to H. So, and thus we can prove that if H is a group, we can prove that if H is a group, then if A comma B belongs to H implies AB belongs to H. And second point is that if A belongs to H, A inverse also belongs to H. And conversely, if AB belongs to H implies AB belongs to H. And next point, if A belongs to H implies A inverse also belongs to H. So this way we can prove this particular theorem. So and then another video clipping, I will give you another theorem proved. Okay, so thank you very much.